Hello friends, how are you? Myself Virendra Kumar and we are going to discuss about a very interesting and useful topics on quantum mechanics. The topic is bound and unbound quantum states. We will discuss about this topic in detail, their physical properties, conditions, symmetric potentials and what are the subtleties for a free particle in one dimensional potential. So let's start the video lecture. What is bound state? In quantum mechanics, a bound state is a quantum state of a particle subject to a potential such that the particle has a tendency to remain enclosed, confined in one or more regions of space. The potential may be external or it may be the result of the presence of another particles. When the potential is due to the presence of another particle, then one can equivalently define a bound state as a state representing two or more particles whose interaction energy exceeds that total energy of each separate particles. In general, the energy spectrum of the set of bound state is discrete. That means in the bound state system, the energy of the particle is used to be discrete. It is not continuous. And also the energy of the particular eigenstate is fixed. Means every eigenstate has its own eigen energy. Okay, although not bound states in the strict sense, metastable states with a net positive interaction energy, but as you know, the metastable states have long decay time are often considered as the unstable bound states as well, and such type of bound states are called quasi bound states. So here you can see in the figure, this is a symmetric potential well, and if the particle is inside this well, that will be confined within this well, and there is a classical turning point at the end of this here, and particle is unable to escape from the potential well if the energy of the particle is lesser than or equal to the depth of the potential well. So bound state can occur whenever the particle cannot move to infinity. That is, the particle is confined or bound at all energies to move within a finite and limited region of space, which is delimited by two classical turning points. The Schrödinger equation in this case admit only solutions that are discrete, means the solutions are discrete. The infinite square wave potential and the harmonic oscillator are the typical examples that display bound states. You can see in this figure, this region is acting as a bound state. You can see here this two boundary, that if the energy of the particle is lesser than V1 and greater than V minimum, that is if the energy of the particle is less than V1 and greater than V minimum, then the motion of the particle is bounded between the classical turning points x1 and x2. The states corresponding to this energy range are called bound states. They are defined as states whose wave functions are finite or zero at x tend to plus minus infinity. So at these positions, the energy wave functions are finite or zero. Usually, the bound states have energies smaller than the potential. That means for a particle to be in the bound state, the energy of the particle should be less than the potential. Well, for the bound state to exist, the potential Vx must have at least one minimum which is lower than V1, that is here V minimum is less than V1. The energy spectra of bound states are discrete. We need to use the boundary condition to find the wave functions by the help of the Schrödinger equation. So friends, to solve the Schrödinger equation for a particle in the bound state, we need boundary conditions. So there are two boundary conditions here at particle at x1 and particle at x2, and another condition which may be used is the normalization condition. So with the help of this condition we can find the solution of the particle in this bound state by the help of the Schrödinger equation. So there are theorems which describes about the bound state system. The theorem states that in one-dimensional problem, the energy levels of a bound state system are discrete and not degenerate. That means the energy of a system in bound state are discrete and not degenerate. Not degenerate means that every eigen state will have its particular eigen values. And second theorem states that the wave function, if it is psi n x of a one-dimensional bound state system, has n nodes. That means psi nx vanishes n times. If there is n node, then psi nx vanishes n times. And if n is equal to 0, correspond to the ground state. And n minus 1 nodes will be there if the n is equal to 1, correspond to the ground state. So examples of ground states. What are the examples of ground states? A proton and electron can move separately. When they do, the total center of mass energy is positive, and such a pair of particles can be described as an ionized atom. But once the electron starts to orbit the proton, the energy becomes negative and system becomes a bound state system, and it forms the hydrogen atom. Only the lowest energy bound state, the ground state, is stable. Other states having energy more than the energy of the ground state are excited states, and they are unstable states. Therefore, they will decay to be stable bound states with energy less than the energy of the excited state by emitting a photon. Next example is a positronium atom is an unstable bound state of an electron and a positron. It decays into photons. Further, it is to mention that any state in the quantum harmonic oscillator is bound but has a positive energy. That means limit x tend to plus minus infinite, potential Vx is equal to 0 for the quantum harmonic oscillator. That means for a bound state, negative energy principle is not applied when the quantum harmonic oscillator energy has a positive value. Such type of systems are like a nucleus is a bound state of, of a proton and a neutrons forming the nucleons. The proton itself is a bound state of three quarks. So you know protons, neutrons are made up of the quarks. So the protons are made up of two up and one down quarks, and each quarks are red, green and blue. So in that case their energies are positive but also they are bound state. However, unlike the case of the hydrogen atom, the individual quarks can never be isolated. But the condition is that the quarks are never found separated, means individual in the nature. They are always found in the form of the proton, neutron. Okay. The Hubbard and Janice Cumming Hubbard models support similar bound states. In the Hubbard model, two repulsive bosonic atoms can form a bound pair in an optical lattice. The JCH Hamiltonian also supports two polariton bound states when the photon atom interaction is sufficiently strong. So these are the examples of the bound states. Now what is the unbound state? Friends, in unbound state, particle is free to move on either side of the potential. It may be on both sides, it may be in one side to free movement. So in case of unbound states, the spectrum is used to be continuous spectrum. So unbound states occur in those cases where the motion of the system is not confined. A typical example is the free particle. That means there is no confinement for a particle. The particle is free to move. In that case, the state is known as the unbound state. For the potential, as you see in this figure, there are two energy ranges where the particle motion is infinite. The first range is E is less than V2 and greater than V1. That means in this range, particle, here there is no boundary. So in this range, the particle is free to move, and also for this range the particle is free to move. So these ranges makes the system as unbound states. So first we will take the case of this when the energy of the system of a particle is lying between V1 and V2. So in this case the particle's motion is infinite only towards x is equal to minus infinite. That is, the particle can move between x is equal to x2 and x tends to minus infinite. Okay, x2 is the classical turning point. The energy spectrum is continuous and none of the energy eigenvalues is degenerate. The non-degeneracy can be shown to result as we will discuss below. Friends, in the case of unbound state, the energy is degenerate. That means various eigenstates can have the same energy. I, I will discuss this in the next slide. So, since the Schrödinger equation is a second order differential equation, so it will give the two solutions, two linearly independent solutions, but only one is physically acceptable. The solution is oscillatory for x is less than x2 and rapidly decaying for the x is greater than x2, so that it is finite at x tending to infinite. Since divergent solutions are unphysical, so we will take only the solution x is less than solution for x is less than x2. So degeneracy comes when the eigenstates, different eigenstates will be having the same eigenvalues. So I will discuss further that how the two solutions are having the same energy. Now take the case of energy greater than V2. That is when the energy of the system, energy of the particles becomes more than the V2 value. So energy spectrum is continuous and the particles motion is infinite in both directions of x, that is x tending to plus infinity and x tending to minus infinity. All the energy levels of this spectrum are doubly degenerate. To the no, it is to be noted that the Schrödinger equation is a linear combination of solution for the Schrödinger equation is a linear combination of the two independent oscillatory solutions, one moving to the left and another to the right. This will also discuss. I will discuss with mathematical uh, descriptions. Now I will discuss about the symmetric potential and unsymmetric potential or non-symmetric potential and the parity. So friends, as we know that there are two solutions to the time independent Schrödinger equations. The first even parity and second is the odd parity. How psi even minus x is equal to psi even x, that is reflection is symmetric in this case. But for the odd parity wave function or eigenstate minus psi minus x is equal to minus psi odd x, and therefore the reflection is anti-symmetric. So as you know that when the potential Vx is even, the corresponding Hamiltonian Hx is equal to minus h cross square by 2m d2 by dx square plus Vx will be also even. Even operators, as you know, commute with the parity operators. Friends, for the parity we will use the parity operator. Now let us consider two cases pertaining to degenerate and non-degenerate spectra of the Hamiltonian. So in case of non-degenerate spectrum, first we will consider that a non-degenerate even operator has the same eigenstates as the parity operator. Since the eigenstates of the parity operator have definite parity, the bound eigenstates of a particle moving in a one-dimensional symmetric potential have definite parity. So for the bound states, spectrum is non-degenerate and discrete, and in this case potential is called symmetric, that is wave function is finite. So now in the case of degenerate spectrum, if the spectrum of the Hamiltonian corresponding to the symmetric potential is degenerate, its eigenstates are expressed only in terms of even and odd states. That is, its eigenstates don't have definite parity. So in case of degenerate spectrum, the eigenstates will have not definite parity. It may be either even or odd parity. The various properties of one-dimensional motion of a particle can be summarized as the spectrum of the bound state is discrete and non-degenerate. The bound state wave function has n nodes if n is equal to 0 is the ground state. Next, the bound state eigenfunctions in an even potential have definite parity. That means if the potential is even, that means potential is symmetric, the eigenfunctions of a bound state have the definite parity. The eigenfunctions of a degenerate spectrum in an even potential don't have the definite parity. Okay, now we will discuss the free particle case and we will solve the Schrödinger equation. Friends, as you know that time independent Schrödinger equation in one dimension can be given by minus h cross square by 2m d2 psi x by dx square plus v x psi x is equal to e psi x. For a particle in free potential, that means if Vx is equal to 0, then particle is free to move. Particle is free. Therefore, in that case, Schrödinger equation reduces to minus h cross square by 2m d2 psi x by dx square is equal to e psi x. This is equation number 1. Now this can be further written as d2 psi x by dx square plus 2me by h cross square psi x is equal to 0. Now put k square is equal to 2me by h cross square. Therefore, this equation can be written as d2 by dx square plus k square into psi x is equal to 0. So, this is the differential equation in the second order and first degree. Therefore, the solution of this Schrödinger equation can be written as in the terms of two linearly independent plane waves. So, two solutions can be given by psi suppose plus x is equal to e to the power I kx and psi minus x is equal to e to the power minus I kx, because d2 psi d2 by dx square plus k square will give the two values. So accordingly it will give the two solutions. Okay, so the general solution can be, the most general solution can be given by the combination of these two plane waves, that is psi kx is equal to a plus e to the power I kx plus a minus e to the power minus I kx. Okay, so this is equation number 2. K square is equal to 2me by h cross square is nothing but the wave number. So here in this equation a plus and a minus are two arbitrary constants, and these constants can be found by the application of the boundary condition. But for the free particle there is no boundary condition, so we can easily get by the normalization condition. So the complete wave function is given by the stationary state psi xt is equal to a plus e to the power I kx minus omega t plus a minus e to the power minus kx plus omega t, which can further be written in terms of the energy or k value, as we know that omega is equal to E by h cross, that is equal to h cross k square by 2m. So this can be written as a plus e to the power I kx minus h cross k square t by 2m plus a minus e to the power minus I kx plus h cross k square t by 2m. Okay, so this is the most general solution for the particle in a continuous state, that is particle is free, where the first term represents the wave traveling into the right direction, while this term represents the wave traveling to the left direction, and intensity of these waves can be given by the square of their amplitude respectively. We should note that the waves psi plus and psi minus are associated with the free particles moving to the right and the left with well defined momenta and energy. So what is energy? You can know here, see that E is equal to h cross omega and P is equal to P plus minus is equal to plus minus h cross k. So we can find the solutions without any restrictions are on k or ae, that is there is no restrictions on the energy and the momentum of the particle So it can have any values. There is no boundary condition. The free particle problem, is very simple to solve mathematically, but it has some subtleties, some minor difference which we must know in this case. The first subtlety is that probability density corresponding to either solution can be given by p plus minus xt is given by the modulus square of the wave function, and that is nothing but the modulus a plus minus square, and this is constant. That means they don't depend on x or on time t. This is due to the complete loss of information about the position and time for a state with definite values of momentum and energy. That means, as we discussed before, the energy and momentum are definite. So, as per the uncertainty principle, we can't locate the particle exactly where the exactly particle is if the energy location as well as the time, if the energy and momentum of the particle is fixed, certain, definite value. And this is a consequence of the Heisenberg's uncertainty principle. When the momentum and energy of the particle are known exactly, delta p is equal to 0 and delta E is equal to 0, there must be total uncertainty about the position and time respectively. And second subtlety is about the discrepancy between the speed of the wave and the speed of the particle it is supposed to represent. That means, in case of the free particle case, the wave speed as well as the particle speeds are not same. We can see the speed of the plane wave psi plus minus xt is given by v wave is equal to omega by k, where omega is the angular frequency and k is the wave number, that is e by h cross k, and that is equal to h cross k by 2m. So on the other hand, classical speed of the particle is given by v classical is equal to p by m momentum by mass, that is equal to h cross k by m. So we see that both are not equal. They are not equal. That means v classical is equal to 2 times the velocity of the wave. This means that particle travels twice as fast as the wave that represent is. So it is not possible. So this is the subtleties in the case of the free particle. Now the third subtlety is that the wave function is not the normalized wave function. How? If we check that normalization condition is fulfilled in the case of this wave function is or not, we find that we will be having as this, and this tends to infinity. So that means the normalization condition is not equal to giving the equality unity value. Therefore the solutions are thus unphysical and is not acceptable. The physical wave function must be square integrable, whereas this doesn't fulfill the square integrable condition. So what is the problem? How can we solve this problem? These problems like the Heisenberg's uncertainty principle and the velocity speed of the particle and wave and the normalization conditions all are not being followed in the case of the solution what we get from the Schrödinger equation. So to get rid of this problem, we can construct physical solution by means of a linear superposition of plane waves. And the answer is given in terms of the wave packet. So if we consider the solution in terms of the wave packets, that is given by psi xt is equal to 1 by square root 2 pi minus infinity to plus infinity phi k e to the power I kx minus omega t dk, then we can get rid of these subtleties where phi k is the amplitude of the wave packet and it is given by the Fourier transform of the wave function psi k is equal to 1 by 2 pi integration minus infinity to plus infinity psi x 0 e to the power minus I kx dx. So we see that the if we keep the solution in terms of the wave packet, it cures all the subtleties which arised. The first subtlety, the momentum, the position, energy of the particle are no longer known exactly. Only probabilistic outcomes are possible. Second subtlety, the wave packet and the particle travel with the same speed, and that is given by the group velocity is equal to p by m, that is group speed or the speed of the whole packet. And third subtlety, that now the wave function is normalized. Thus we see that the if we are taking the wave function in terms of the wave packet instead of the plane waves, individual plane waves, then the all the conditions like Heisenberg uncertainty principles, normalization conditions, as well as the group the speed of the plane waves and the particle wave, all are fulfilled. So friends, these were the things that I wanted to discuss in this video lecture on the bound and unbound quantum states, and I hope that you enjoyed this video lecture and learned about the bound and unbound quantum states, their physical properties, and how we solve the problem for the solution of the free particle. And we also get to know that the bound state will be having the non-degenerate state, and spectra is discrete, as and also the unbound state will be having the continuous spectra, and they will having the degenerate state. So friends, if you like this video, press the thumbs up and share this video with your friends and colleagues so that they can also learn about this video lecture. So friends, if you have not subscribed this Sai Academy channel, please subscribe it right now and press the bell icon so that you can get the update of any upcoming videos on time and you could not miss the video. Thank you friends.